Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School, a boarding school for boys in rural Virginia. It's sad here without the students, but our campus is a beautiful refuge while the world ends and then comes back from ending. Please come visit us in the after times. I really mean that. Now, remember, I love every one of you dearly. My job and my calling is to support all of us as we prepare for this one-off weirdo administration of the AP Physics 1 exam. There are many, many people behind the scenes working long hours to ensure that you are able to show off your physics knowledge and thus earn the credit and placement you've hoped for all year. Yet, I'm starting to hear way too much panic and pearl clutching from students and from teachers too. We need to stop with the automatic knee-jerk complaints. People are hearing, for example, that the calculus exam, not the physics exam, provides a list of helpful keyboarding suggestions for equation input. Oh, wait, that's not fair. How can I be expected to learn to keyboard so quick, say the physics students. Wait, so we have to derive equations? I thought we didn't. Will they take off points if we use a different format? I heard some random dude on TV say that we'll be on lockdown for 4 more years. So do I also have to learn these tips for my undergraduate thesis defense? Please stop. And tell your teachers and your parents to stop too. Nitty-gritty details about the exam taking process will be coming to you fast and furious in the next week or so. You do need to keep up to date by making sure you have logged into your College Board account, by reading everything on the AP coronavirus page, by paying a careful attention to all emails from your teacher and from the College Board. Soon, you'll even be able to try out the official AP exam platform on which you'll submit your actual answers. Do that. I tried a sample of it this morning. It was fun. It worked. I submitted a story about Edna. After that, though, please relax and learn physics. If you know physics well, then the exam format, whether you type or write your responses, which exact kinds of questions are on the test, that won't matter. Yeah, pay attention to the official College Board sources so that you get correct information. Yes, call out your friends or teachers who spread misinformation. But in the end, who cares about all that? Just build your physics skills. Have fun interacting with other physics students who are doing the same. If you'd like some suggestions direct from an insider who's also the most awesome physics teacher in the country, then please go to my blog, search Jacobs Physics. Matt Scaler of Long Island, the associate chief reader and a development committee member, posted some clear advice about the best way to approach the exam platform. Read that. It's from someone who knows. And now, ignore all the speculation and rumors. The official motto of the AP Physics reading applies here. Everything is going to be just fine. To the physics. This is our schedule for today. We are talking about the 2017 AP Physics 1 Problem 3, which is a qualitative-quantitative translation. Qualitative-quantitative translation is one of the 2 questions you are going to get. It's a style of question. The style of question means they are going to suggest a physical situation and some mathematics that underlie that physical situation, and you are expected to show what features of the mathematics apply to the features of the experimental situation. If you'd like to go to @JacobsPhysics on Twitter, you can give me some comments, questions, stories, and I'll answer them. Little this afternoon, little tonight. Brad Williams is probably on there already answering now. Here's the question. It's long, it's got 5 parts. We're going to go part by part. Let's start with the beginning. If you see the picture, we have a disc that's hitting a pivoted rod. And the rod is pivoted at the end. And the first question is, assuming the rod is much more massive than a disc, so this is like a peanut and a heavy baseball bat, I want to give the rod as much angular speed as possible. Where should we fire the peanut at the rod? Over here or over here? All right, I'm going to answer experimentally first. Now, I know you can't do this on your AP exam because you don't have this set up, but I can do this. Look what I got here. This is just a rotating platform. It's not pivoted at the edge, it's pivoted at the center. So pretend this is the pivot and this is the rest of the rod. Here is position C. Notice that I have 2 pieces of clay here. Those pieces of clay are so when I fire this yellow ball, that the ball hits and just drops straight down. It doesn't bounce off. Hopefully, maybe one of these can stick, but it won't always stick. All right, let's put this on. And now let's fire. First, I'm going to fire to the left of C, to this position. Ready? And fire. Okay, moved a little bit. Now let's fire to the right of C. And you can ask yourself right now, if you need to, pause the video. Do I think I'm going to get more or less or the same angular speed right here? Ready? Look at that. I clearly got more angular speed when I went to the right of point C, when I went as far as I can to the right. Why is that mathematically? Why is that in terms of physics principles? Well, we know that torque is equal to the force that I apply times the distance from the fulcrum, the lever arm. And in the case where I went to the right of C, that lever arm was bigger than when I fired to the left of C. There was more torque exerted on the rod. Another way to think about this is through angular momentum. We know that angular momentum is conserved. Before the collision, the angular momentum of the yellow ball is the only angular momentum that's there. And that angular momentum transfers into the rod. Well, there's more angular momentum the farther from the pivot we are, because the angular momentum of a point particle is mvr. R is the distance of closest approach to the pivot. So either way, we're finding out that to the right of C is what makes sense. And sure enough, that jibed with our experiment. Let's go to part B now. This is qualitative quantitative translation. In part B, we're told that a student finds the following equation for the post-collision angular speed, how fast that thing was rotating after the collision. And we're not asked to derive that. We're not asked to say anything at all about where that came from. All we're asked is, does it make sense based on our answer to A? Our answer to A was, we need to fire the disc at the rod over here to the right of the center of the rod. Does this make sense based on that fact? Well, let's see. X is the variable used to represent the distance from the pivot that the disc hits the rod at. Where is that X? That X is in the numerator. These other things, the mass of the disc, the initial speed of the disc, and the rotational inertia of the rod are not things that change. The only things that the thing that changed or could change is this X. The bigger the X in the numerator, the bigger the omega also in the numerator. Therefore, there's this relationship mathematically means that a bigger distance here should provide a bigger angular speed, which is exactly what I said in A. That is the best answer to the qualitative quantitative translation. Let's look at the rubric for this part now. This is Greg's 6-word rubric. This is not the official rubric. This is just how I think of awarding points here. Part A was worth 1 point for the right answer as justified with either torque or angular momentum. No points in part A for the wrong answer. Part B, you get 1 point just for the consistent check mark. That's unusual. In most AP Physics 1 exams, you do not get any points just for checking a box. But in this case, we said if you check the correct, that is the consistent box, then you will get a point. And then 1 point for reasoning correctly, relating the mathematics to what you already said about the experiment. Let's try this rubric with a couple of examples. And here I'm going to once again enlist the help of my pet hippopotamus, Edna. Here she is. And Edna, could you please help me grade this one right here? You'll have to come over here. This student says to the right of C, that's the correct answer, but we don't get any points in the first part for just checking the correct box. We have to justify it correctly. The angular speed is largest when the disc hits the rod to the right of C. Okay, that just repeats the question. We don't have to say that, because it will have the largest distance from the pivot. Okay, that's true. That's just restating what the problem says. That's not a point yet. Thus providing the most angular momentum, as angular momentum equals mvr for an object moving linearly relative to a point. Okay, now Edna says we can give that point because that person has the correct answer and correctly justified with reference to angular momentum. So 1 point here. Now to part B. Did the student check the consistent checkbox? Well, the correct answer is in this part to the right of point C. And then the correct answer in part B is, since X and W or X and omega are linearly proportional, then the answer is yes. Okay. They did get the correct checkbox. Is this correct, Edna? Because X is in the numerator, it is directly proportional to omega, angular speed. If you increase X, you will increase omega. That person is now making a mathematical reference that justifies the experimental discussion that they had previously. That is full credit. Thank you, Edna. I'm going to have a bunch of these because I want you to see exactly what, I think it's really important that you see today how we look at qualitative, quantitative translations. Bertha is going to help out now. Here's Bertha, and Bertha's paper that she's grading says, to the right of C, that's correct. By hitting the block to the right of C, we said that, the lever arm from the pivot increases. Ah, that increases the torque of the disc on the rod. There we go, causing the rod blah, 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 blah. That's all I need to hear because the torque of the disc on the rod will be bigger because the lever arm is bigger. Good enough. Thank you, Bertha. Now, what about part B? Does the student check the correct box? Yes. Does the student then refer mathematically to the features of this equation that support the reasoning here? The speed is directly proportional to X, which was established in the last question. Okay, that's all we need to see. That's good enough right there because that's the mathematical relationship and they've already talked about the experimental relationship. But wait, I have to keep reading. Bertha's going to keep going because if this student then contradicts him or herself, or says something incorrect, or tries to give me a second answer, then we grade the response that's incorrect. You can't game the test by saying, well, it could be this or it could be this, hoping to cover your bases. That doesn't work. We choose the answer that earns less points. But let's see. In addition, it is proportional to the V0 and mass of the object, which makes sense because the total angular momentum of the ball will become the total angular momentum of the system. Okay, that's not wrong. It's totally irrelevant here, but it's not wrong. Omega should finally be inversely proportional to I because rotational inertia resists the change in angular acceleration. That's also true. So we're all good here. This person still gets the second point. Bertha can award that point, but Bertha would have really preferred, because she has to read 10,000 of these, Bertha would have really preferred that all that stuff went away. Briefly explain really does mean one sentence. All we needed to know was that omega was proportional to X in the mathematics. And in the previous question, we said that that meant that bigger X means bigger omega. All right, Anthony. Anthony is not a nice hippopotamus, according to Edna. Anthony is going to grade this. And Anthony's paper says, to the right of C, okay, that's right. The mass hitting the rod at the right and having the pivot on the opposite side would result in having more angular velocity without having much opposing force. Does that reference torque or angular momentum? No, it does not. So it does not get the point. But wait, can't you do the problem a slightly different way? Can't we accept a different answer if it's correct physics? I was the table leader. And I was in a group of a bunch of table leaders and a bunch of readers, and none of us came up with any appropriate way to solve this problem without reference to torque or angular momentum. I'll still read this and I'll realize there's nothing here about physics. That's not correct. Part B. Did they check the correct box? Yes, Anthony, you have to give them that point. Yes, I know that this response was silly, and when we read this, it's going to be silly as well. But in this case, they got the point for checking the correct box. That's very rare, but that is showing physical reasoning here. The student understood somehow, some way, even if they couldn't express themselves well, they did understand that by hitting to the right of C, that equation corresponds to that because of the proportionality. They might not be able to tell you why, but they at least knew that this box is correct. Yes, because it gains all the force of the disk, distance, and initial velocity and divides it by resistance of motion and equals the velocity and having less opposing forces. I don't know what that means, but they get 1 out of 3. All right, Anthony, stay put. I got one more for you. I know you like grading these ones that don't get a lot of points, because Anthony is a mean hippopotamus. More force is necessary to open a door. Wait a second, why am I even reading this, Anthony? This person said to the left of C. That's the wrong answer. In this particular problem, we stop reading when we see the wrong answer. Is that always true? No. There are plenty of AP exam questions where it doesn't matter if you check the wrong box. You can get most or full credit. Remember the paragraph response problem we did the other day with the object on the spring? Who cares what box you checked? We still read the whole thing. In this case, though, you had to check the correct box to get the first point. It depends. Can you predict that? You can't game the exam. We come up with these rubrics on the spur of the moment. Well, okay, not on the spur of the moment. It's not like we go sit down to grade each day and say, okay, here's today's rubric. But we create these rubrics well after the exam is given, and they are carefully thought through by a whole bunch of people. You cannot predict what the rubric is going to ask. All right, so Anthony, look, yes, you still have to look at part B. Did the person check the correct box? Anthony, he did. The student did check the correct box. But wait, Anthony says that the correct answer is yes, this is consistent with to the right of point C. The point is given here for a consistent checkbox. If this student thinks that you're going to get more angular speed by hitting the rod to the left of point C, that is closer to the fulcrum, well, that person's wrong. But if the person honestly thinks that, then that person should be telling us that this is an incorrect equation. I said we needed a small x, but in this equation, bigger x means bigger omega. That's correct. This person has identified the feature of the mathematics, x in the numerator, that leads to x being bigger for bigger angular speed. And they recognize that, well, that's not consistent with my answer there. So Anthony, you got to give them both points, one for the consistent check and one for the reasoning. You don't have to be fully correct to get credit. You do have to use authentically valid physics reasoning, though. All right. Now, let's go on to part C. We're going to do more qualitative quantitative translation because this problem is possibly the most QQT problem ever created. It's wonderful. 6 of the 12 points are directly related to the skill of discussing an equation, discussing a physical situation, and then showing what parts of each relate to each other. In part C, another student deriving an equation for the post-collision angular speed makes a mistake and comes up with this. Without deriving the correct equation, how can you tell this equation is not plausible, that it doesn't make physical sense? And explain briefly. We are not being asked to do a derivation. In fact, we're told explicitly this equation is wrong. But a good physicist can look at an equation and just look at the dependence of the variables, the relationships mathematically, and tell you whether that makes physical sense or not. So how is this graded? This gets 1 point for referring to functional dependence. That is, the student needs to be talking about what is in the numerator, what is in the denominator, and how being in a variable in the numerator or the denominator would affect the angular speed. They shouldn't be talking about, well, you'll see some wrong things that are there, but they shouldn't be talking about anything except that functional dependence. 1 point then is for focusing the argument mathematically on either the rotational inertia or the mass, because those are the points that are incorrect about these dependencies. And then 1 point for using physical reasoning. Mathematics, physics. Those are your 2 points here. So let's look at some samples again. I will write the equation out nice and big right here so you can see it. There's a simplified version of the equation so you can see it. Now, Edna, you're going to go first because you always get the good ones. Here is Edna's to grade. In this equation, if you increase the mass of the disk because it's in the denominator, it will decrease the angular speed. Well, the mass of the disk is in the denominator. That'll decrease the angular speed. This person has talked mathematically about that relationship. Now this person needs to talk physically about that relationship, which makes no sense, as a larger object should provide more momentum and therefore more omega. This person has done the thought experiment. This person has said, oh yeah, well, I know that if there's more mass, then that should give me a bigger angular momentum, like we kind of talked about before, so mass shouldn't be in the denominator. All 3 points. All right, Bertha. Bertha is an elephant. She is Edna's best friend. Here you go, Bertha. Bertha's paper says, it does not make sense, is not possible. That doesn't get you any credit here, but because we already said that this answer doesn't make sense. Because the parts of the equation are multiplied wrong. I is multiplied by x rather than d to the 4th, and m disk. Well, does that get us our first point? No, that's not talking about functional dependence. That's just talking about what should be multiplied together and what shouldn't be multiplied together. That's not what we're talking about. We need to be talking mathematically about the relationships. Is something in the numerator or the denominator? Is something directly proportional or inversely proportional? This does not make sense. Okay, also, this shows an inverse relation between omega and m disk and a direct relationship between omega and I. Oh, well, that's nice. That does talk about mathematically the relationships. Problem is, I'm seeing 2 answers here. I'm seeing this person telling me the parts of the equation are multiplied wrong, and this is how they should be multiplied. And then I'm seeing also there's an inverse relation. There are 2 answers. The student is trying to give me 2 answers to cover their bases. I can't accept the second answer because the first one's wrong. I have to choose the one that earns fewer points. This one would have earned 2 points right here. This one earns nothing because it's not talking about functional dependence. It's not talking about the mathematical dependence of I or m disk, and it's not, nowhere does anything talk about the physical relationship. So, sorry, Bertha, you're not allowed to give any of those points. So I'll give you another problem, Bertha, that you can grade. I, or rotational inertia, has the unit kilogram meters squared. X has the unit m, meters. Okay, this is all about units. And this person is saying if you multiply the units out, you don't get units of angular speed. Okay, this is not correct. First of all, the person did the unit multiplication wrong. If you do the unit multiplication, you're going to find the correct units for angular speed on this side. This person made a mistake. But the problem is a unit test is bare bones basic stuff. That's like congratulating somebody for remembering to breathe today. Of course, our expressions have to make sense units wise. That's just a typical assumption that anybody doing physics knows that. We shouldn't be checking that. We should be checking the physical dependences. We should be checking whether something's in the numerator or in the denominator and what that means mathematically and what that means physically. This person didn't do any of that, so nothing. And I know that there are going to be those of you out there who are going to come in on Twitter and argue with me and say, well, wait, but doesn't that show, I'm just telling you, this is like the umpire calling balls and strikes. You can argue with me about where the outside corner of my strike zone is or should be, but I'm telling you, it's consistent. I call strikes that are a little off the outside corner and a little off the inside corner. The pitchers know, the batters know, it's consistent every time. So don't argue with me when I call a strike on the outside corner. That's just the way it's going to be. So let's stop arguing and let's play baseball. This is how qualitative, quantitative translations are going to be graded. It does make sense. So let's talk about how we can do this process of relating mathematics to physics every time, because you will get the credit every single time if you can just understand how mathematics relates to physics and focus on those things. So what other things can't we focus on? Anthony wants in, because Anthony prefers, he's a mean hippopotamus. He prefers to see the ones that don't get a lot of points. Dividing the product of I times v naught by m disk d to the fourth would be such a small fraction and would not result in having the most angular velocity. Nope, 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 nope. We need to be explicitly addressing whether I is in the numerator or denominator, or whether mass is in the numerator or the denominator. No credit here. And one more. All right, Anthony, can we find a point to award here? Notice this person crossed this part out. I'm not even looking at it. Right or wrong, doesn't matter. Anthony, you're not allowed to read it. It's crossed out. And in fact, I've trained my brain that when I see something crossed out, I truly do not read it. All I'm going to look at is this. Because the rotational inertia of the rod is an impediment to changes in angular velocity, that's a reasonable, that's a very reasonable definition of rotational inertia. I like that one. Impediment to changes in angular velocity. It should not be directly proportional to the angular velocity. Oh, look at that. We talked about the physical meaning of rotational inertia. That's the physics part. We talked about the proportionality between rotational inertia and angular velocity. That's the mathematics point. And we are talking about the proportionality. We are talking about whether rotational inertia is in the numerator or the denominator. So we get the third point. Yes, Anthony, you have to award those points. And I know that Edna thinks you're a mean hippopotamus, but I think that you are a hippopotamus with integrity who will give these 3 points. So we can take you to the reading. All right, part D. Part D asks, don't assume the rod is much more massive than the disk. And it says, we're going to derive an equation for the post-collision angular speed of the rod. This was great in 2017, but in the end times, while the horsemen ride, we ain't going to be doing any derivations. Well, I'll still show you how this was derived, but I'm going to go on very quickly. Best way to derive this is to use conservation of angular momentum. Indicate that means the angular momentum of the disk before the collision, because the rod is stationary, is equal to the angular momentum of the disk and rod together after the collision. Let's write an expression. Well, they told you the expression for the angular momentum of the disk to start with. We know that angular momentum is I omega, and we know that rotational inertias are additive. So we add rotational inertia I of the rod plus rotational inertia of the disk, which was given, and there we go. Solve for omega. You're not going to have to do that because you can't type that. And best physics teacher in the country, Matt Scaler, says you should be typing your answers, he thinks. All right, so how am I going to change this problem? If I were on the committee, which I'm not, I want to be very clear on that. This is just how I would reappropriate this problem for the new age of AP exams this year. I want to rewrite part D. I'd say something like, without manipulating equations, explain how you would go about deriving an expression for the post-collision angular speed omega of the rod. I don't know. I'm not saying that's going to show up. I have no idea whether that's too much math for the exam. I'm just telling you that this is something we can type. And I've typed it out for you. On the original rubric, we gave 4 points. And I'll apply those 4 points here. One was for stating conservation of momentum explicitly, either L equals L or in words. One, recognizing that the system angular momentum beforehand was this. One, recognizing the system angular momentum afterwards is I omega. And then one for plugging in the correct rotational inertia of the system. So that's all 4 points. Notice that there's no point for the correct answer. That happens sometimes. It's not always the case that we have to get the correct answer to get full credit. There's a reason I went through that. So let's go through, without manipulating equations, explain how I would go about deriving an expression for this angular speed. I'm not asked to derive an expression. I'm asked just explain how I would do that. I don't have to get the answer according to this rewriting of the exam problem. So let's see what I wrote. Angular momentum L is conserved in the collision. That would have been the first point there. Before the collision, the only angular momentum is that of the disk, mv0x. Notice that I wrote just v0. I didn't put any subscripts in there. Is that okay? Sure, I can read that. I know exactly what that means. If I had used an O instead of a 0, would you have taken off points? Folks, we don't take off points. The question is, have you communicated enough information for the reader to understand that you know what you're talking about for one of those 4 points? And absolutely, I know what you're talking about there. After the collision, the objects are stuck, so the angular momentum is just one term, I omega. That is their combined I. Okay, we know that the angular momentum afterwards is I omega. Rotational inertias are additive, so the combined I is this. Wait, isn't the reader going to think that this is 2 times mx? Aren't they going to take off points? Once again, I know exactly what you mean there. There's no way you'll be writing 2 times m times x there when the problem stated that the rotational inertia of the disk was mx squared. I know what you mean. Now, would it be nice if you had written mx with a little caret too? Yeah, that's a little more clear, but I know what you mean. We're not going to be lawyers. We are going to be physicists. Physicists grade your exam. So communicate as you would to a physicist. The responsibility for communication is still on you. If you write something that's truly ambiguous, I'm not going to read into that to say, oh, well, I know what this student means. I don't know what you mean. But I am not going to stand on ceremony and said, well, this person wrote a W instead of the Greek omega, so that person couldn't possibly know what they're talking about. Well, I think she's talking about weight. No, we aren't idiots. All right, set L before equal to L after and solve, and there we go. All right, let's go to the final part of this problem. The final part of this problem is consider the collision for which your equation in part D was derived, except now suppose the disk bounced backwards instead of sticking. What happens to the post-collision angular speed? Does that rod move faster when the rod sticks or when the rod bounces off? Well, let me give you the answer, and then we're going to do it. There's 2 ways to go about the answer. One is to talk about impulse. Impulse is the change in momentum. When something bounces, it experiences more impulse than when something sticks because the speed, both the thing that stuck and the thing that stopped had to change their momentum to 0, but then the thing that stopped had to continue changing its momentum to bounce. If you want to think in terms of negatives and positives for directions, the final minus initial momentum, that is the impulse of something that bounces, is some amount of momentum minus a negative. That gives you more change in momentum. Another way to look at this is that the system angular momentum is, in the first case, this way. Therefore, even after the collision, the system angular momentum has to be the same amount this way. If the objects stick together, great. If the objects bounce, then the disk has a momentum this way in the backwards direction. So the rod has to move even faster in the forward direction to cancel out that momentum that's backward. Momentum is a vector. So either of these approaches is correct. Now, do you believe? Do you really truly believe that when the disc bounces off the rod, that the rod's going to move faster than when the marble sticks? I don't know. Let's see. Here, I'm going to stick the marble to the rod. It might not physically stick. It did once in rehearsal, but it often just bounces straight back down. And that's fine. That's the same thing. You ready? Boom. 1, 2, 3, 4, 5, 6. Took almost 6 seconds to to twirl all the way around there. Let's take the clay off. Now, this thing is going to bounce off and come straight back. Ready? 2, 3, 4, 3.5 seconds this time. In other words, when the marble bounced, it imparted more angular momentum to this thing. It changed its momentum by more by bouncing backward, and therefore the rod had to change its momentum by more, and the rod moved faster. Isn't that amazing? I love setting up AP Physics questions in the lab. All right. We will do a quick version of the fundamentals quiz because I've had good feedback on these. Here's our fundamentals quiz. Once again, please pause the video, answer the questions before I go over them. Yes, seriously, pause it. Have your answers written before I go over these. Under what circumstances is average velocity equal to, just add the two together and divide by 2? That's only when A, the acceleration, is constant. Otherwise, the average velocity is the displacement over time interval. B, define torque. Torque is force times lever arm. You might write that as force times distance from a fulcrum. That's acceptable too. That's what a lever arm is, after all. Define period. It's the time for one cycle of harmonic motion. You might be thinking of period as the time for one full wavelength to pass. That's true. That's if you're talking about waves. If you're talking about simple harmonic motion, it's the total time for one complete cycle. D, give one criterion to determine whether a vibrating object is in simple harmonic motion. I'll give you 2. The position time graph is a sine or cosine. Or you could say that the restoring force is linear with displacement. What does that mean? That means basically F equals kx. The restoring force, that is, there's a force that points back toward the center, and that force gets bigger as the displacement gets bigger, where when that displacement doubles, the force doubles as well. Either one of those is a condition for simple harmonic motion. E, give the equation for rotational inertia of the point object. Well, we just had that today, mr squared. In the problem we did, r, the distance from the fulcrum, was given as x. F, a 40 Newton force acts on an 8 kilogram object. Well, I thought A is F over M. So shouldn't that be 40 Newtons over 8 kilograms? Well, A is net force over mass. If there are other forces acting, then there could be a net force that is not 40 Newtons. G, define acceleration. Acceleration is the change in speed every second. All right, technically that's for linear motion when something's moving in a straight line. And technically that's the change in velocity. You need to take the direction into account. And when something's moving in a circle, you need to take into account that acceleration can change direction. Great, but if you're just looking to tell yourself, what does acceleration mean? And to differentiate what is acceleration and what is speed, because you all get that confused all the time. Just remember, acceleration is the change in speed every second. That's the simplest version to tell yourself, shorn of all complexities. H, how do you determine an object's displacement from a position time graph? Well, on a position time graph, the vertical axis tells where something is located. So the displacement from here to here, from this time to this time, is reading the vertical axis and then subtracting the vertical axis values at 2 times. I, the units of angular acceleration. Well, linear acceleration is the change in speed every second. So that's measured in meters per second. Angular acceleration is the change in angular speed every second. So that's measured in radians per second. Wait, Greg, can't I write radians per second squared? Of course you can. Now, tell me what a second squared means. Real quick, come on, tell me physically what a second squared means. It's mathematically equivalent. I prefer that you think of angular acceleration as being measured in units of radians per second, because that tells you how many radians per second of speed are gained or lost every second. And then, is angular momentum a vector or a scalar? What does that mean? Angular momentum is a vector. It means the direction matters, like in our problem today. Whether the angular momentum is this way or that way makes a difference. And K, state the equation for gravitational force of one planet on another. Gm1 m2 over d squared. Careful not to differentiate that, or careful not to confuse that with the formula for a gravitational field or the gravitational, or just anything else that's just gravity, mg, things like that. This is the gravitational force of one planet on another. All right, it is time, friends, for me to go to Twitter, and I have time for about 2 or 3 questions today, if you'd like. I have a class after class today. I have a class for my school, and I will be back on Twitter in the neighborhood of 1:30, but I'll try to answer a few right after this. But let's take some questions right now. I have a bazillion notifications. Let's see. Blah, 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 blah. Yeah, Brad is answering a question. Somebody is talking about, well, wait, can't you just check units? And I'm telling you, that's a bare bones expectation. On a quantitative qualitative translation, you have to talk about the dependence, whether of a variable, whether the variable is in the numerator or the denominator, and what that means. And Brad is pointing out that through the AP Institute, through all the literature, if you read the curriculum guide, you will see that that is a requirement. Just checking units is not acceptable. If you don't believe me, you can try putting units on there, but you won't get credit. If you don't like that, then you can come to the reading, and I am happy to have you discuss with a bunch of experienced AP Physics people. And the problem is you're probably not going to win that argument because we've been through it and talking at long lengths about, well, is talking about units good enough for qualitative quantitative translations? And our conclusion is it is not. All right. Let's see here. And that's exactly what I'm talking about of, we need to stop with the complaining and the, well, I wish the College Board would do it this way. Okay, well, I wish frogs had wings so they didn't bump their butt on the ground every time they hopped. It's not the way the world is. I wish my students were back here in my lab with me. I miss them. That's not the way the world is. So let's adapt the best way we can. So let's go on here. Brad Williams is doing all sorts of good stuff here. Okay. Liliana asks, why would hitting the ball to the right of C create a greater angular speed after the collision is what we're talking about, if angular speed is equal to linear velocity over radius? Isn't increasing the distance of C increasing R? Great question. That equation that you cite, Liliana, angular velocity equals V over R. That's not really applying right here. That's for if I want to know something's going around a circle every second. So that's 6 radians per second. But I know the radius of that circle. What is the speed if I were to put a radar gun on that object as it moves around in a circle? That's what that equation's for. In this case, the angular speed after collision cannot be simply set equal to V over R because we've got a collision here. We have to do conservation of angular momentum and all kinds of things to figure out what that speed would be. But I can, in a shorthand, say, I know that there's more torque if I apply that force farther from the fulcrum than closer. So I can be pretty sure that I'm going to change the angular momentum of this system more by putting the force out here than out here, applies more torque. I could also talk directly about angular momentum. All right, one more, if I can find one here. Oh, I don't, because I have Wanda and Roosevelt giving me their daily question about what did I have for breakfast. They wrote it in Hebrew today. They wrote it in Thai yesterday, or maybe it was Vietnamese and I responded in Thai. They wrote it in Russian the other day. They're using Google Translate very well. Wanda and Roosevelt, I had a cup of coffee for breakfast, and I've got something waiting for me after lunch. I don't know what it is. I want to give a nice shout out to Jeff Clarion of Oregon. He's a fantastic physics teacher. He was the cruise director for the AP Physics reading back in the day. He used to organize our softball games. He used to organize our game nights. It was a lot of fun. And he and I were on a call with the Men in Blazers the other day for all the teachers who wanted to talk to some internet celebrities who talk about soccer on their podcast. It was loads of fun. Folks, I would love to talk to you about AP Physics. Go to my Twitter, @JacobsPhysics. Go to my blog. You can read what Matt Scaler had to say. Tomorrow, Josh comes back with you. And tomorrow, Josh comes back with you with this problem. Going to have to come in 2 halves. Here's the first. There's the first half. Screenshot that if you like. This is, if you want to look it up online, this is 2017 problem 4 on the Physics 1 exam. This is the second half. He will be explaining this to you and going through all kinds of his expertise. He is a great physics teacher as well. I will be back with you on Friday, and then we will talk on Friday about what next week is going to look like. Next week it's going to be different, and it's going to be fun. I hope you will join us for that and everything. So until Friday for me, until tomorrow for Josh, and for my pet hippopotamus, Edna, her friend Bertha the elephant, and their sort of friend Anthony the mean hippopotamus. This is Greg Jacobs signing off and saying, so long, everybody.